The previous video we had studied about percentage composition and how much of a particular element is present in that compound. In this video we are going to be studying about empirical and molecular formula. But before I go on and talk about what the definition of each of these is and what it all means, we will be studying it with an example. Okay, so observe what I write and think what they mean. Okay. Okay, so the first we have is hydrogen peroxide. Its molecular formula is H2O2. Its empirical formula is HO. Second is the molecular formula of water, which is H2O, and empirical formula is also H2O. Molecular formula of benzene is C6H6, whereas empirical formula of benzene is just CH. Molecular formula of glucose is C6H12O6, and the empirical formula is CH2O. Now, in all of these cases, molecular formula is giving us the number of atoms. Okay, exactly how many number of atoms are present is given by the molecular formula. Whereas the empirical formula, all we're doing is it gives us the simplest whole number ratio. So here, if you divide it by 2, this thing becomes HO. So all we are doing is you're getting the simplest whole number ratio of various elements which are present in the molecule. Okay, so all here C10H8. So divided by 2 divided by 2. So 2 5s are 2, 4s are 8. Here 6 1s are 6 2s are and 6 1s are. So CH2O. C6H6, 6 6. Both of them are the same, so CH. So the empirical formula is giving us the simplest whole number ratio. Now the basic interconnect, or rather the basic way you can understand as to how they are different is molecular formula would be equal to N into the empirical formula. Okay, and N is equals to the molecular mass divided by the empirical formula mass. So, if N equals to 1, then the molecular formula will be equal to the empirical formula. That's exactly what has happened with water. So, the molecular formula will give us the information of the exact number of, or it gives us the true formula of the molecule, and it expresses the actual number of atoms, which basically means H2O2 has 2 atoms of hydrogen and 2 atoms of oxygen. And the empirical formula is the simplest whole number ratio of various elements which are present in one molecule of the compound. So empirical formula of hydrogen peroxide is HO. This does not mean hydrogen peroxide has just 1 atom of hydrogen, 1 atom of oxygen. No, this is the simplest whole number ratio. Okay, so now we need to be able to calculate the molecular formula and the empirical formula from the percentage composition. Okay, so the steps to do that is given in the description box. I would suggest you like open it, right? And we will be doing a few problems for us to understand the various steps better. Okay, suppose you have a compound which contains 4.07% of hydrogen and 24.27% of carbon and 71.65% of chlorine, and its molecular mass equals to 98.96. So we need to figure out what its empirical and molecular formulae are. Okay, so this can be done by the following steps. First, we need to okay, so first what we'll do is we'll write this in a form of a table. Okay, so element, okay, percentage composition. Okay, so the element is, let's take carbon. Carbon's percentage composition is 24.27. Next, hydrogen, whose composition is 4.07, and chlorine, Cl, whose composition is 71.65%. Okay, so this is the first thing. Now, the first step is given as divide the percentage of the element by its atomic mass, which will give us the number of moles of atoms of the element in the compound. So, the moles of the element, we've already done this, is the percentage of the element divided by its atomic mass. Okay, so moles of the element is nothing but the percentage of the element by the atomic mass of that element. Now, the atomic mass, I'm taking it as, now carbon's atomic mass is 12, hydrogen is 1, and chlorine is 35.5. Okay, now what we need to do to find out the number of moles of the element, we are to find out the number of moles of the particular element, we have to divide this by this. So 24.27 divided by 12. 4.07 divided by 1 and 71.65 divided by 35.5. Okay, now this is again because when we spoke about the moles of the element, we are also spoken about its individual mass. Here we are considering the percentage composition, which just means that in 100 grams of that compound, this would be the percentage of that individual element. So we are using the same formula, and by simplifying this we will get 2.02, and next you will get 4.07, and you will get 2.02. Now we need to figure out, now this is the first step. Now the second step is divide the result obtained in the above step by the smallest value amongst them to get the simplest ratio of various atoms. So what do we have to do? We just have to divide what we've gotten in this column by the smallest value. Okay, here you have 2.02, 4.07 and 2.02. Out of these three, 2.02 is the smallest. So we need to divide all these three values with 2.02, and this will give us the mole ratio. Okay, so 2.02 divided by 2.02. Similarly, 4.07 by 2.02 and again 2.02 by 2.02. So all we're doing is we're calculating the simplest mole ratio, and you will get 1. Here you will get 2.01. Here you will get 1. And 2.01 can be rounded off to 2. So this mole ratio will give us the empirical formula, which means the empirical formula is equals to C1K H2Cl1. Okay, so that's what is the the fourth point. Write the symbol with the respective numerical value of each element on its right. So this is how we are able to calculate the empirical formula from the percentage. Let's go over this once and so that it will be clearer. First, we are given the percentage composition of 3 elements and the molecular mass of a particular compound. Now, we are taking the individual elements and the percentage compositions. The percentage composition divided by the atomic mass will give us the number of moles of that particular element. And we are taking the smallest number, and in this case it was 2.02, and dividing it with that, dividing all the 3 values with 2.02 to get us the mole ratio. Now sometimes what will happen is the values might be, so here 2.01 was the value for hydrogen, and we could easily round it off to 2. There might be cases where you might not get it in such way. In that case, we need to multiply it by a same number. All the 3 will again be multiplied with the same number for us to get it in terms of a whole number. That's why it was very clear. Nearest whole number. See, the 0.3 was make the values obtained above to the nearest whole number and multiply with a suitable integer to make the values whole. And this gives us the simplest whole number ratio. So here we've gotten the empirical formula. Now let's calculate the empirical formula mass. So you have 1 carbon, so that's just going to be 12, and you have 2 hydrogens, so 2 into 1 plus chlorine is 35.5. So this will give us the empirical formula mass as 49.5. Now remember n of a particular substance. We need to find out n because molecular formula will be equal to n into the empirical formula, and n is also equal to the molecular mass by the empirical formula mass. So the next step we have to do is calculate. So we already calculated the formula, empirical formula mass, which is step number 5. Next we need to determine the molecular mass. In some cases you won't be given the molecular mass, you might be asked to find out in various ways, and in that case you'll have to do that, but here you have been given it as 98.96. so here, and then you need to determine the value of n. So n equals to the molecular mass 98.96 divided by 49.5. Now after simplifying this, you will get 1.9999, and this is approximately rounded off to 2. Okay, so the value of n is 2, which means the molecular formula will be equal to C2 H2 into 2, which means H4Cl2. Okay, so once again we'll go over the steps. First we had figured out the mole ratio from the percentage composition. Okay, then we had figured out the empirical formula and its mass, and n value equals to the molecular mass divided by the empirical formula mass, which over here is 2. So we divided this value by this one, and so we have to multiply this into this and this, which gives us C2H4Cl2. Okay, one more important thing, you need not write 1 over here when there's no value, so you could have just we can just write it as CH2Cl. I hope this was clear, but if it isn't, we will be doing another problem, and instead of writing the problem and basically I'm going to be reading it out, yeah, and going to be writing down what was the given items. Okay, so an organic compound gave the following composition. Okay, so when an organic compound was analyzed, this was the following results that they found. They found that carbon percentage is composition percentage is 57.8%, hydrogen is 3.6%, and the remaining was oxygen. Now the molecular mass was given as 166. Feel free to pause the video right now and try and solve it on your own. But if you're not able to and you want to see another problem being solved, stay. So element. So you have 3 elements: oxygen, carbon, and hydrogen. So carbon, hydrogen, and oxygen. The percentage composition. So the percentage composition of carbon is given 57.8. Next, for hydrogen is 3.6, but for oxygen it's not given. Okay, so you just have to add these two. So 57.8 plus 3.6. Okay, this gives us about 38.6 and sorry, I'm so sorry. 3.6. Okay, this minus 100, and when you simplify you will get 38.6. Okay, so to write it better, I would maybe write it as this: oxygen percentage would be equal to 100 minus 57.8 plus 3.6, that gives us 38.6%. So 38.6 is the value for percentage composition of oxygen. Now first step is for us to write down the the atomic masses. So let's write that down. Atomic mass of carbon is 12, of hydrogen is 1, of oxygen is 16. Next, we need to calculate the moles of the atom. Okay, so that's done simply by dividing this value by this one. So 57.8 by 12, 3.6 by 12, 38.6 by 16. Oh, sorry, by 1. I'm so sorry. This is the atomic mass of hydrogen. Now after you simplify it, you will get 4.82, 3.6 and 2.41. Now the next step is slightly, I wouldn't say tricky, but you need to focus when you do it. So here what we will be doing is we have to divide all these 3 values with the least one. So here the value of 2.41 is the least, right? So the mole ratio will be calculated by 4.82 by 2.41, 3.6 by 2.41 and 2.41 by 2.41. This gives us 1, this is the easiest. Now the other 2 are simplified and we get 2 and 1.49. Now our ratio for the empirical formula is supposed to be a simple whole number ratio. So I can't just say C2H1.49 and O. Do you think this will be right? Because 1.49 will mean there is 1.49 part of hydrogen which exists, which is not possible. So this is wrong. So which means we need to convert this into another set of digits, which will give us a simple whole number ratio. So these three values are rounded off by multiplying it into 2. So this will give us the simplest whole number ratio as 4 and 2.98, which is approximately equal to 3 and 2. So this means the empirical formula is C4H3O2. Okay, so here we did the same thing as the previous problem, but the only difference over here is that we have taken the mole ratio to convert it into the simplest whole number ratio, because 1.49 just cannot be there for that empirical formula. Okay, so this is the empirical formula. Next we need to calculate the empirical formula mass. That will be equal to 4, right? So 4 into 12 plus 1 into 3, or 3 into 1, plus 16 into 2. Okay, and this when simplified will give us the value of 83. Now we've been given the molecular mass as 166. So N will be equal to the molecular mass divided by the empirical formula mass, that is equal to 2. And when N equals to 2, this has to be multiplied. So the molecular formula equals to C8H6O4. Okay, so in this problem we had just taken the percentages. We were given the percentage of carbon, hydrogen, but not oxygen. So we had to subtract and figure it out. Okay, then we had taken the percentage composition and divided it by atomic mass. The reason we find out that is because we need the number of moles. So the number of moles is then further divided by the smallest value of the three. Okay, so we are taking the least value, and here in this problem, unlike the previous one, we had gotten 1.49 and we need a simple whole number ratio, because of which we are multiplying it into 2. Okay, so then after that you are able to get 4, 3 and 2, and that gives us the empirical formula. From there you were able to calculate the molecular formula by just calculating the empirical formula mass and the molecular mass, which is already given. So the molecular formula is this one, which gives us the exact number it gives us the exact number of elements which are present in that particular compound, whereas empirical formula will give us the simple whole number ratio. And this way we are able to find out from the percentage composition the molecular formula as well as the empirical formula. That's it for now. Do check out the next video, which is going to be about stoichiometry.